The compression dictionary registry is a subsystem responsible for managing dictionary instances across distributed compression operations. Each dictionary maintains a set of predefined byte sequences and corresponding token identifiers. The registry provides lookup, insertion, and synchronization operations. Dictionaries are organized by namespace and version. Access patterns follow a read-heavy distribution with occasional flush operations during cache rotation cycles. Dictionary instances are stored in memory-mapped files with a 16 MB default allocation size. The memory layout consists of a fixed header section followed by variable-length entry segments. The header contains format version, entry count, timestamp of last synchronization, and checksum information. Entries are packed sequentially without padding to minimize disk footprint. Accessing entries requires traversing index metadata in the header region. Lookup operations perform binary search across the index region. Search keys are hashed using a consistent hash function defined in version 2.3 of the specification. Hash collisions are resolved through linear probing with step size 8. The lookup procedure reads the header first to obtain entry count, then positions the search within index boundaries. Average lookup time is logarithmic in dictionary size. Insertion operations require exclusive write access to the dictionary file. The system acquires a file lock prior to insertion. New entries are appended to the end of the entry segment after verifying that available space permits the write. The header entry count is incremented atomically. If space is insufficient, insertion fails with an error code indicating dictionary full status. No automatic growth or reallocation occurs. Entry format within the dictionary consists of a fixed header with key length, value length, and flags, followed by the key bytes and value bytes in sequence. Key length is stored as a 2-byte unsigned integer. Value length uses 4 bytes for future expansion. The flags field indicates compression type and whether the entry has been recently accessed. This metadata allows the system to filter entries during synchronization passes. Synchronization operations occur when dictionary instances across multiple nodes require consistent state. The registry initiates a sync event by reading the last synchronization timestamp from each dictionary header. Entries modified after this timestamp are identified and transmitted to peer instances. Peers apply updates in timestamp order to maintain causality. Failed synchronizations are logged and retried after an exponential backoff interval. Eviction policies determine which entries are removed when the registry needs to reclaim memory. The least recently used policy tracks access timestamps for all entries. When eviction is triggered, entries with the oldest to access timestamp are selected for removal in priority order. Entries marked as persistent are never evicted. The eviction process removes entries one at a time until memory targets are achieved or all non-persistent entries are exhausted. Namespace partitioning allows the registry to maintain separate dictionary collections for different compression contexts. Each namespace has its own file on disk and independent in-memory cache. Namespace identifiers are 8-byte values. Operations include create namespace, delete namespace, and list namespace. Creating a namespace reserves disk space and initializes header structures. Namespaces can be marked read-only to prevent modifications. Versioning allows multiple dictionary versions to coexist within a single namespace. When a dictionary is modified, a new version is created with an incremented version identifier. Clients can explicitly request a specific version when performing lookups. Older versions remain available until an explicit cleanup operation removes them. Version metadata includes creation timestamp and base version reference for efficient storage of incremental changes. Checksum verification ensures data integrity across storage and network operations. The registry computes a CRC32 checksum over all entry data in the dictionary. The checksum is stored in the header region. When a dictionary is loaded or after synchronization, the checksum is recalculated and compared. If values do not match, the system logs a corruption error and may trigger recovery procedures or return error status. Cache coherence protocols ensure that in-memory representations of dictionaries remain synchronized with disk state. When a dictionary file is modified externally, the in-memory cache may become stale. The registry implements a write-through cache model where updates are immediately persisted to disk. Read operations may service from cache if the modification time on disk has not changed since the cache entry was created. Performance monitoring collects statistics on registry operations. Metrics include lookup success rate, average lookup latency in microseconds, insertion success rate, eviction frequency, and synchronization latency. Statistics are recorded in a circular buffer with configurable window size. The registry provides a query interface to retrieve aggregated statistics over specified time intervals. This data is used for tuning and capacity planning. Error handling follows a consistent pattern throughout the registry. Operations return status codes indicating success or specific failure conditions. Failure codes include dictionary not found, entry not found, insufficient space, synchronization timeout, and checks a mismatch. The registry logs failures to a persistent log file with timestamp and context information. Clients must check return codes before assuming operation success. Configuration parameters control registry behavior at startup. Parameters include default, dictionary size, maximum namespace count, eviction policy selection, cache size limit, and synchronization interval. These are read from a configuration file in TOML format. Invalid parameters cause startup failure with detailed error messages. The registry validates all parameters before initializing internal structures. Configuration changes require process restart. Cleanup operations manage disk space and remove obsolete data. The cleanup procedure iterates through all dictionaries and removes entries marked for deletion. Older dictionary versions can be consolidated into single versions to save disk space. Cleanup operations can be invoked manually or scheduled to run during off-peak hours. Progress is reported incrementally as cleanup proceeds through the registry. The registry shutdown process follows an orderly sequence. Pending operations are allowed to complete with a configurable timeout. All dictionaries are flushed to disk, ensuring consistency. Synchronization connections are closed gracefully. Memory structures are deallocated and file handles are released. The shutdown completes when all resources return to unallocated state. This ensures that subsequent startups will find the registry in a valid state.